Okay, dear students, this is Professor Varun, and welcome to my mathematics class. And this is the chapter of mathematical induction. Let us first of all understand what is the principle of mathematical induction, what it actually does, what is the concept behind this, why are we doing what we're doing in this chapter. Okay. So first of all, you see, there is some preposition that is given to us. For example, it is written here. This is one example given here. One divided by one into two, one divided by two into three, one divided by three into four, plus one divided by n into n plus one, and this is equal to n divided by n plus 1. So this is a kind of preposition, and we don't know whether it is right or wrong. It is just given here. We need to prove that this is right. But how can we do that? You see, what is written for all the values of n. So you will say that, okay, let me prove it for n is equal to 1. Let us take n is equal to 1, and I'm calling it p1. And I substituted n is equal to 1 here. So what am I getting here? 1 divided by 1 into 2. And on the right hand side, I would be getting 1 divided by 1 plus 1, that is 1 by 2. So on both of the sides, like right hand side and the left hand side, we are getting the same value. So I can always say that yes, the preposition is true for n is equal to 1. But the claimant is saying that this proposal is correct for all the positive integers. And now you said, okay, let us try for n is equal to 2. And then you tried it for n is equal to 2, and surprisingly, you found it to be absolutely correct. How? You see, if n is equal to 2, so I would be like, there will be two terms here. So it will be 1 divided by 1 into 2 plus 1 by 2 into 3. And from this place, you would be getting 2 divided by 2 plus 1, that is 2 by 3. And when you solve this thing, you actually find it to be true. Still, you cannot say that yes, it is true for all the positive integers. You can't say that because we have not even tried for the other. So what you do is we go for 3, we go for 4, but for how many such variables, for how many such values will we keep on calculating things? So this is where mathematical induction comes into way, and it says that no, 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 I will tell you how to do this. So, what is the principle that is being used here? What they do is they first of all take it for k, that n is equal to k, and then they create one equation, and then they just assume it that okay, fine, we assume that for any value that is k is the element of positive integers, any integer you can choose, and let us assume that this is correct. Now if this is correct, by having this condition that this is correct, we will create another equation for pk plus 1. And when we create this equation, that is pk plus 1, we have to prove that this is right. Now, if I prove that this preposition is right, I would be doing in upcoming examples, do not worry. If I prove that this is right by using the condition that pk is right, this is my assumption. So I can say that yes, p1 was right, it means it should be right for 2. And if it was right for n is equal to 2, it should be right for n is equal to 3. If it is right for n is equal to 3, it should be right for n is equal to 4. Why? Because you have proved that p of k plus 1 is right if p of k is right. I repeat, if p of k is right, if it is assumed that it is right, p of k plus 1 is proved to be right. It only means that if p of 1 is correct, it is correct for all the positive integers coming after it. If it is correct for 1, then our proposal says that it will be correct for 2. If it is correct for 2, it must be correct for 3. If it is correct for 3, it must be correct for 4. So this is the principle of mathematical induction. And in the next video, we are going to try some of our questions. Okay then, all the best.